Morena, I'm James Power. This year I've been working on a project regarding export debarking and sort of optimizing three parts of the supply chain. So a bit of background before I start. Logs are the third largest export in New Zealand. They represent 62% of the harvest volume, and that's been increasing for the last 15 years and forecast to remain high until around about 2030. So what that translates to, as you can see up in the top corner there, is a lot of logs. All of those logs have phytosanitary requirements on them to limit the spread of pests such as these bark beetles. Historically, the main method for doing that has been methyl bromide. Methyl bromide is being phased out because it's ozone depleting and highly toxic. So to replace that, what we've got is phosphine, which is a fumigant that's applied in the holds of ships while the ship's in transit, and debarking, which is applied to the logs that are above deck, because obviously you can't fumigate logs above deck because the fumigant will blow away. So this project, the overall goal of the project has been to help exporters optimize the supply chain of debarked logs. There's been three parts of this. Throughout my research, I've noticed that no one had published data on the size and the utilization of the log ships coming to New Zealand, which is actually really important for the debarked supply chain, because utilization is the reason that we load debarked logs onto ships in the first place, to entirely utilize the weight that a ship can carry. And it also helps to forecast the volumes that are going to be required. So my second point, my supervisor over summer had noted that debarked volumes were fluctuating seasonally. That's because logs dry out more in summer than they do in winter en route to the port. So a ship can carry a certain weight, but because the logs are less dense, you're getting more volume on the ship. And this third part is finding the impact of diameter and size on the maximum production a debarker can output. So three parts of the debark supply chain that I wanted to try find things that can be improved. So back to that first section. This is a histogram of the sizes of log ships that sailed in New Zealand over the past 3 years. As you can see, there's really clear defined classes, particularly these two. These represent handy size and handy max. So we've got down in the bottom corner there, we've got a handy size ship. Outside the range of this graph, we've also got a few ships at 90,000 tons, which is a recent development. Post-Panamax is what they're called, and a couple of really small ships, 20,000 tons. But for the most part, they're in really defined classes, mostly around this 35 and 40,000 ton mark. Yeah, so just note how there's virtually no ships in between these classes. But if we look at loading, the loading graph is a lot more spread out, which was largely because of this graph here, which, oh, I clicked the wrong computer. So these smaller ships, the smaller classes, load almost to their maximum weight. So they load to about 97%, and the remainder of that might be fuel, it might be other variable loads that the ship carries. But these larger ships here don't load nearly as much. And the reason for that is they don't normally have stanchions to carry logs above deck. And that's shown in this graph here. Oh, gosh. What's happening there? That's shown in this graph here. So most ships, handy size and handy max, like I said, these are the two most common classes. On the side there, you've got Panamax and post-Panamax, the larger classes of ships, which carry a much lower proportion of debarked volume. Moving on to the next section now, which was the seasonal variability in the volume of debarked timber carried. You can see this is the weight factor, so the density of the logs as they arrive at the port, based on weighbridge data. And you can see that it definitely does vary seasonally. So logs arrive 9% heavier in winter in the North Island ports than they do in the summer, and 6% for Port Chalmers. So this yellow line at the top here is Port Chalmers. You can also see that Port Chalmers has heavier logs year round than the other ports do, which is interesting because Southland in Southland, the wood density is the lowest out of the country. So what that shows is that because the climate is colder and damper in Southland, the logs are drying out less. So we expect to see the same trend in this next graph, whereby there's less volume being loaded in winter than there is in summer. But what you can see there is that it's really, really variable. But if we cut out this bottom section of the data, you can see the trend is still there. But as expected, there's less volume being carried in summer from the middle of the graph than there is in, say, March. Based on that, taking the average of each month, a key output of this project was a model that I created. So what I've done there is, like I say, take the average of each month. So say you had a ship that arrived in July. It's now coming in February. You could take the volume that arrived on the ship in July and multiply it by 1.11, and that should be approximately what you would load on the same ship returning in February. So that hopefully will enable exporters to more accurately forecast the volume that'll be carried, and volume of debarked timber that'll be carried on the ship. And finally, the debarking section of the project. Data for this section was from the Murupara debarker. It was very variable. So to model what the impact of length and diameter should be in an ideal debarker, I created this model of a linear production line. So each of these lines on the graph is an increase in diameter, and then on the x-axis there you've got an increase in log length. So if, say, I increase from a 0.2 meter diameter log to a 0.4 meter diameter log, double the diameter, you get quadruple the volume output. But if you increase the log length, I've got 2.4 down this end and 2.4 meter log down this end of the graph, a 12 meter log down this end of the graph. You can see there's very little increase in volume. Now that sort of disagrees with the results from the actual debarker, that where the length of the log had a similar impact to the diameter of the log in terms of the production. So that sort of identifies the gap between the logs as creating more delays than what was expected. So that's sort of a key thing that could be looked at in the future for increasing the production of a debarker. So in conclusion, 3 key points. From the utilization graphs, we can see that there's room for more debark volume on those larger ships. There's a few issues with that. Obviously, we'd have to add stanchions to those larger ships. Would need better optimization of the port storage volumes, because there's more. You'd need to put more volume on one ship. So it'd probably only be possible at larger ports like Toto. Second point, in order to better forecast the volume of debarked timber that would be required throughout the year, I created a model that enables you to take a previous sailing of a ship and convert it to a future sailing in a different month of the year, based on that seasonal variability that I was talking about. And thirdly, log length in a debarker had more impact than we expected. So that's an area that the debarker operators could focus on in the future.